large. Okay, let's look and see how can I make a function here. If I want to do f of x colon x squared, oh, sorry about that. Keep forgetting the f of 2 is 4. So if I do, I can put in, I don't have to have this jammed up against each other. That still works. This is a colon, then an equal sign, and then it repeats it there, but then you can see I can put in f of, say, 4, and I get out 4 times 4 is 16. So it enables you to put in. So what you want to do is in Wx maxima is end up with P of n being, some formula that has n in it, because then you can answer all the questions in the project. Yeah, I give it here. All the project here, you can answer all these questions just by calling this P of n function for different n's. So the problem is to find that function, which basically means to extend this idea to arbitrary n and work out what the formula is. So you have all the tools to do that. So I'm going to let you do that for next time. Okay. There is that, and we have a little bit of time left to sort of begin our next topic, which is conditional probability. And let's consider something called, this is a preview of what we'll do next week, which is conditional probability. And what it has to do with is the idea that there's connections between events, that if you know one event has occurred, then that changes the probability. And there's connections between events where some events are mutually exclusive and some events are independent, and we're going to get simpler probability formulas for their connections. So this is the topic here is connections between events. Okay, so what we'd like to know is the probability that event 1, let me call it just that event A occurs. Can't spell today. That event A occurs given that we know that event B occurs. And although this doesn't answer what we mean by this, we're going to give a name to it. We're going to call it the probability that A occurs given that B occurs. So this vertical bar means given that, instead of such that. Or you could think such that B has occurred. Okay, so this is called a conditional probability, because it's not the probability that A occurs, it's the probability that A occurs given that some other event has occurred. So this is just the name that we're going to use for it. We don't have yet a definition. Okay, so the best thing to do is look at a model, and the text uses a model where it imagines a box like a that's like a big box, and it has like little egg cartons that you could see in the bottom that are sort of like these grid squares. And I imagine that it imagines that there's like, uh, um, um, well, let's look at the particular um, situation in the text. Here's our model. We have a box with little. We're imagining we're going to drop a marble in here and let it rattle around until it goes into one of these little corrugated squares. And so there's like the way I've drawn it. There's like I think 10. Um, 2, 3, 4, 5, 6, 7, 8, 9, 10, or something like that. There's a certain number. I'm thinking of these. Well, actually, I'm drawing them with a larger, this isn't the full size, but I'm thinking of this as there being, 10 and 10 and 10. So it's like there's 100 over here and 100 over here. So I can sort of visualize this as in the left box here, there's going to be 100 little squares. It could be on the right 100. So I have these, the event would be I throw the marble into this box and it lands in one of these 100 spaces on the left. And that would be the event left, so that that the then probability that's in the left is going to be 100 over 200 to 1/2. And the purpose of this diagram is to illustrate that the size, we can represent the numbers of elements by the area covered. So for example, the probability by the counting is 1/2, but you can see the left half here covers 1/2 of the right. So you can sort of see the probability of the event L as sort of the size, the area that that event covers in this simple example. Okay, well then we have like, here's a quarter and here's 3/4. And you can see the probability that that you have the marble lands in the first quarter is 1/4, and the probability it lands in the complement in any of in quarter 2, quarter 3, or quarter 4 is going to be 3/4. Okay, now how about this one? Well, and we're ignoring that this is going to be corrugated, right? So we have the diagonal top event and the diagonal bottom event, and with the corrugation. So there's going to be, if this divides them in 1/2, that there's going to be 100 up here and 100 here. So the probability of each of these is 1/2. And we will also, here's two other events, top and bottom, right? Each 1/2. So these are all different events that we've defined. And the question is, there's several different possibilities that would be connections between different events. And one circumstance is, consider the following situation where I have a bunch of events laid out, which you have the left event, the right event, you have Q1 and Q2, and then there's the middle. And the middle is sort of Q2 and Q3. Well, Q1 and Q2 are 1/4, and the probability that's in Q1 is the same as the probability it's in the second quarter, which is 1/4. The probability it's in the middle, which is 2/4, is going to be 2/4, or sort of 1/2. Now, but the question is, let's say we want to know the probability that that we knew it was in the middle. Let's say that we knew that the marble was, say, thrown into the box and it was covered up. So we didn't know where it was in the middle, but we could see that it wasn't in Q1 and it wasn't in Q4. But the question is, what's the probability it's in the left? Well, we can say, well, in some sense, we want to know it's not in here. So we want to, what we actually know is, since it's in the middle, we were asking the number of outcomes, given that we know it's in the middle, is going to be the number in the left, given it's the middle, is going to be this quarter here. which is the intersection of L and M, which is quarter-2. So what we're going to mean, this is part of trying to motivate the definition of conditional probability, is that it's going to be the number that are in the middle, and it's in the left. Well, that's an intersection. So we're going to define the probability as the number that are in the middle intersected with the number in the left over the total number of ones in the left. So it's, in some sense, instead of having it this the fact that it's in the middle and the fact that it's in the left, the probability it's in the middle, I said it backwards. The probability that's say we know it's in the left and we know the probability it's in the middle. Well, since we know it's in the left, that sort of becomes our new sample space size. So in some sense, this, given that it's L, we know that sort of can become our new sample space size, and that given L and M, that means that it has to, we know it's in L, we know the probability it's in M. Well, that's the intersection of M and L. So what we're going to mean by the probability of M given L, which is this notation, is going to be this fraction of the probability of the intersection, the chance that's in both, divided by this sort of reduced sample space size here. Now, this is a motivation for in the end, this is how it's defined. Now, I can take this definition and put it in a more universal form or more useful form by dividing both numerator and denominator by the same number. That doesn't change the value. These two are equal by some fraction formulas. And so as a result then of doing this, we see this top one here is the absolute probability of the intersection divided by the probability it's on the left. So that becomes our definition, that the probability that let me go back here. Given the model in the text, the probability that A occurs, given that B occurs, is going to be the probability that A is going to be the non-conditional probability that A intersection B occurs over the probability that B occurs. So it's the second one that's the denominator, and you have the intersection in the numerator. So now if we wrote out our classical probability definitions, this would be the number that's in the intersection divided by the sample space size over the number that's in B divided by the sample space size. Well, if I simplified this by saying, well, this is, and I wrote that as a union when it should have been intersection. This is just like, a fraction, 5/6 equals 5 times 1/6, just pulling the numerator out front. That's all I'm doing here is pulling the numerator out here, and then over here I can do the same thing in the denominator. But you can see that then this is like 1 over S, 1 over S. I can cancel them top and bottom, and I end up with A intersection B over B. So I tried to motivate this as the definition, then run this backwards, but this is what the definition of what we are going to mean by conditional probability. And then there's going to be different sort of situations that result, a lot of counterintuitive situations where what you know affects the probability of some other event occurring. In particular, this is relevant to the other two probability puzzles that we have.